Hello guys, my name is Celso. In this tutorial video, I will talk about the transformer element. In special, the focus will be given to the Y-primitive calculation method implemented in OpenDSS for this element, including a few examples. Let's start with a single-phase two-winding transformer. The nodes of the primary side and the secondary are labeled in capital letters and lowercase, respectively. And the first and second nodes of each terminal are labeled with and without an apostrophe, respectively. The primary side contains N1 windings and the secondary contains N2 windings. I will consider its short circuit impedance ZCS connected to the secondary. Let's also label the nodal voltages and the injected currents of this element. Both of them will use the subscript W as a reference to winding and also the corresponding node. For example, the current injected into node A, primary side, is IWA, and the current injected into node A', secondary side, is IWA'. The same applies for the nodal voltages. For example, the voltage of node capital A', primary side, is labeled as VWA'. Usually, the short circuit impedance is given in a per unit basis. Then, ZCS in actual ohms can be calculated as ZCS in per unit times ZB2, that is the base impedance of the secondary side, and it is calculated as V base square divided by ST, where ST is the rated power of the transformer. The first part of the process is to consider the short circuit impedance in either a 1 voltage base or 1 turn base, like the following. The 1V in brackets notation means in a 1 voltage base. Keeping the notation, this nodal voltage can be named as V capital A 1V and the other one as V lowercase a 1V. The current flowing through the short circuit impedance is named as ISC. The currents flowing in each winding, pay attention to their direction, are named as I capital A 1V and I lowercase a 1V, and the voltage drop across the short circuit impedance is VAA in a 1 volt base. The actual value of the short circuit impedance in a 1 volt base can be calculated in the same manner, but considering a voltage equal to 1. Now we can start to build the Y-primitive matrix of this element. First, we can say that IA in a 1 volt base is equal to the short circuit current and I lowercase a is equal to minus the short circuit current. We can write these two relations in matrix form. The voltage drop across the short circuit impedance is V capital A minus VA. This relation can also be written in matrix form. The column vector representing the currents flowing in the 1 voltage base windings can be written as I1. The column vector that represents the coefficients that relates I1 and the short circuit currents can be written as B. Then we have the following expression. We can do something similar for the voltage drop equation. We can say that VAA is B transposed times a column vector V1. That is also equal to the short circuit impedance times the short circuit current. As I1 and V1 are injected currents and nodal voltages respectively, what would be a nodal admittance matrix Y1 that relates these two column vectors? First, we have that I1 can be written as B times ISC, and according to this expression, V1 can be written as the inverse of B transposed times VAA. Based on the same expression, ISC can be written as YSC, the inverse of ZSC, times VAA. Then we can say that Y1 is equal to B times YSC in a 1 voltage base times B transposed. At this point, Y1 is a nodal admittance matrix on a 1 turn or 1 volt base. There is no wiring connections represented, pretty much like a per unit model, commonly used for positive sequence power flow. Now let's include the windings. In order to do so, let's equate the currents injected in each node of the initial single-phase transformer model with the injected currents in the short circuit reference frame, I1. Applying Ampere's law, we can find these four relations. Which can be written in a matrix form like the following. The same applies for the voltages. The actual injected currents vector into the windings will be named as IA, and by naming the matrix with the number of winding turns as N, we can write that IA is equal to N times I1. Similarly, for the windings nodal voltages, we can write that V1 is equal to transposed N times VA. Now, we can relate the windings injected currents and nodal voltages with other nodal admittance matrix called YW, that stands for winding admittance matrix. Let's find this matrix. IA can be written as N times I1, and VA can be written as the inverse of N transposed times V1. Then we can say that the winding nodal admittance matrix is N times Y1 times transposed N, or N times B times YSC times transposed B times transposed N. At this point, YW is a nodal admittance matrix of an element that is somehow floating. By floating, I mean that this transformer is actually not connected to any bus of the system. Thus, it is still necessary to relate the winding currents IA to the terminal currents, and the winding nodal voltages to the terminal voltages. In a simple case, like the single-phase transformer, the relation is pretty easy. In a matrix form, we simply need to multiply an identity matrix and the winding currents vector in order to find the terminal currents. The same applies for the voltages. This identity matrix will be called as A for the currents and transposed A for the voltages. The reason being is that for this case, as A is an identity matrix, there is no difference between A and A transposed. However, the most generic expression uses A for the currents and A transposed for the voltages, as we will see further in the same video. Finally, the terminal currents can be called as Y primitive or Y prime, and terminal voltages can be called V primitive. The goal of this method is to calculate the transformer Y primitive matrix, which is responsible for relating I primitive and V primitive. Then, writing I primitive and V primitive as function of the non-matrices, we can find the general expression for Y primitive, that is A times N times B times YSC in a 1 volt base times transposed B times transposed N times transposed A. Beautiful, isn't it? At the end of the day, all you need is the short circuit impedance of each pair of windings and the turns ratio or voltage ratings of the windings. The incidence matrix A can be derived based on the connection of the transformer to its terminal. Now, let's understand how we can specify the transformer parameters in OpenDSS. Let's start with the short circuit impedance. It can be written as a resistance plus a reactance. In OpenDSS, the resistance can be specified by using either the parameter percent load loss or percent %RS, which contains the pair percent %R1, percent %R2, the per unit resistance of each winding, whereas the reactance can be specified through the parameter XHL or XLH for a two-winding transformer. What is the relation between percent load loss and the transformer series resistance? Neglecting the transformer magnetizing branch, its model in per unit is essentially a series impedance called ZSC. The total series resistance of the transformer is percent %R1 plus percent %R2, and XHL represents the impedance measured from the high to low side of the transformer, or between the high-low pair of winding. In OpenDSS, these three parameters, percent %R1, percent %R2, and XHL, are defined in percent values. Percent load loss is basically the power that is dissipated in the transformer series resistance when it's full loaded. Then, percent load loss is exactly the same as percent %R1 plus percent %R2. In order to convert percent load loss to actual kilowatts, all we need to do is to divide it by 100 and multiply it by the transformer rated power. Now, let's go to OpenDSS and create a single-phase 2-winding transformer. It will be called TR. It is a single-phase transformer with 2 windings. Let's set its XHL to 5, then percent load loss to 5, and the ppm anti-float, percent no load loss, and percent imag to 0. The last 2 parameters will be explained soon. The ppm anti-float parameter is responsible for grounding all nodes of the transformer. It's essentially the value of a tiny impedance connected to each of the transformer's nodes. It is important to use this parameter when one of the sides of the transformer has no path to ground, which can make the nodal admittance matrix of the system not inversible. By default, this value is set to 1. You can find a full explanation of this parameter in the PDF called Modeling the OpenY-OpenDelta Connection in the OpenDSS docs folder. Now, we have to specify the connection, the voltage level, and the rated power for each winding. Note that as the first winding is connected between nodes 1 of bus A and the ground, by default, the rated voltage across the winding corresponds to a line to ground voltage. Let's solve the system and run the dump debug command. In this report, you can check all the properties of this element. In special, at the bottom of the page, you have access to the matrices ZSC, Y1, and YW, used in the Y primitive calculation process. Note that only the lower triangle of these matrices are shown. Let's take ZSC for example. This is a single-phase transformer. Then, there is only one series impedance. How has this value been calculated? We know that ZSC in a 1 volt base is equal to ZSC in PU times Z base in a 1 volt base, where ZSC in PU is equal to R plus JXHL, and Z base is 1 over ST. R is equal to the load losses, that is 5%, and we also set XHL to 5%. Then, as the rated power of the transformer is 50 kVA, we have that ZB is equal to 0.05 plus J 0.05 times 1. Remember that ZB is a 1 volt base over 50,000 VA. That is exactly equal to 1 plus J times 10 power of minus 6 ohm. At the end of the calculation process, this is the final Y primitive matrix. You can also define the load losses by using the parameter %RS. As I've shown earlier, percent load loss is equal to percent R1 plus percent R2. Then, for example, setting both percent R1 and percent R2 equal to 2.5, we should get the same Y primitive matrix. If we set percent R1 to 5 and percent R2 to 0, we get the same Y primitive matrix as well. Going back to our base case with XHL equal to 5 and percent load loss equal to 5, let's now explore the parameters percent no load loss and percent imag. We have already modeled the series impedance of the transformer. Both the no load losses and the magnetizing reactance are modeled as a shunt impedance connected to the second winding defined. Let's call this impedance as ZOC, which stands for open circuit impedance, and that corresponds to an admittance YOC. This admittance can be broken into a conductance GOC and a susceptance BOC. The conductance is directly related to the parameter percent no load loss, and the susceptance is directly related to the percent imag, or magnetizing current. The relation is pretty simple. Percent no load loss is equal to 100 times GOC times V squared, and similarly, percent imag is equal to minus 100 times BOC times V squared, because, as we know, the magnetizing impedance has an inductive nature. The values of GOC and BOC are calculated for the rated voltage, 1 pu. As a consequence, percent no load loss is equal to 100 GOC and percent imag is equal to minus 100 BOC. Then, as this element is connected in shunt, after the calculation of the Y primitive matrix through the method described earlier, the admittance YOC is added in the Y primitive matrix between the nodes of the second winding. In our case, for instance, let's assume both percent no load loss and percent imag equal to 10 and solve the system again. We can verify that the Y primitive matrix has changed only in the last 2x2 submatrix, which is the submatrix that contains the two nodes of the second winding. What I'm trying to say is that Taking our transformer model in per unit, if we connect an admittance between its nodes 3 and 4, we know that this admittance should be added to the self-admittance of these nodes, y33 and y44, and subtracted from the transference admittance between these nodes, y34 and y43. Let's take the admittances y33 and y34 as an example. Before the addition of the no-load loss and %imag, they were equal to the following values. And after the addition of those parameters, by taking the difference of these values, we can get the value of YOC. Now, let's calculate YOC according to our expression. GOC in per unit is equal to % no-load loss divided by 100. That is equal to 0.1 pu. As %imag is equal to 10, BOC in per unit is minus 0.1. We also know that Z base is equal to V base square over X base, and by consequence, the base admittance is equal to S base divided by V base square. The transformer rated power is 50 kVA, and as the magnetizing impedance is considered connected to the secondary side of the transformer, V base is equal to 4.16 kV. Then, by multiplying GOC plus JBOC in per unit by the base admittance, we get that YOC is exactly the value we were expecting. Now, let's talk about a three-phase transformer in a Y ungrounded delta connection. This transformer is built by considering three separate single-phase transformers in which their nodes are connected according to the three-phase connection. In the first terminal, nodes A, B, and C should be connected to three different nodes. For example, nodes 1, 2, and 3 of bus A, respectively. And for a Y ungrounded connection, nodes A', B', and C' should be connected to each other to an isolated node of bus A. For example, node 4. In the second terminal, as it is a delta connection, we should connect the adjacent nodes, and then each point of interconnection should be connected to a different node of bus B, like the following. In this case, ZSC in a 1 volt base becomes a diagonal matrix containing each of the short circuit impedances in a 1 volt base. Matrix B can be written as a diagonal matrix as well, where each of its non-zero elements is equal to a column vector 1 and minus 1. Similarly, the N matrix can be written as a diagonal matrix where each of its non-zero elements has the same format of the matrix N for the single-phase transformer. Now, matrix A can be written by looking to the relation between the currents injected in each winding, in red, and the currents injected in each node of each bus, in green. One can easily find the following relations. Which can be written in matrix form, like this. Then, the matrix A, in this case, is the following. With the matrices ZSC, B, N, and A, Y primitive matrix can be calculated by using the same final expression we have used for the single-phase transformer. Back to OpenDSS, let's change the number of phases of our transformer TR to 3. The no-load loss and the magnetizing current to 0, the rated voltage of the first winding to 115 kV, and clearly specify the nodes of bus A and the connection of each winding. By running and solving the circuit again, we can note that ZSC is now equal to 3 times 10 power of minus 6, whereas in the first case it was just 10 power of minus 6. The reason being is that now there are 3 ZSC elements and we haven't changed the load losses and XHL compared to the single phase case. In this case, ZSC for each single phase transformer within the three-phase transformer model must be calculated such that the total losses are equal to the value specified in the % load loss parameter. Then, this impedance can be calculated considering that each of the single-phase transformers will handle a third of the total three-phase power of the transformer. Then, we can say that ZSC in a 1 volt base is equal to ZSC per unit times 1 square divided by st over 3. That is equal to 3 plus 3j times 10 power of minus 6, exactly the value shown in the dump report. The final y primitive matrix is the following. Note that it contains 8 nodes, 4 nodes in each terminal, because, as mentioned in the y primitive and y matrix video, OpenDSS forces the number of nodes in each terminal of these elements to be the same. As the secondary of this example is connected in delta, we can see that the corresponding row and column of the fourth node of this terminal has been filled with zeros. Finally, we can also verify the addition of the no-load losses and the magnetizing current for this case. Remember that both of them are added in the secondary of each single-phase transformer. Then, in this case, we have an impedance ZOC between nodes A and A', B and B', and between nodes C and C', all lowercase. These three impedances can be seen as a three-phase load connected in delta. For a three-phase load connected in Y, we can say that the base impedance is the line-to-line voltage square divided by the three-phase power of the transformer. And by using the Y-delta conversion, we can say that there is a base impedance for a delta connection, which is 3 times the base impedance for the Y connection. Let's set, for example, a magnetizing current of 10%. Solving the circuit, one can verify that only the 3x3 submatrix related to the 3 nodes of the secondary side of the transformer have been changed, as expected. Furthermore, only the susceptance matrix has been changed, because we haven't added any no-load loss to this transformer. The susceptance related to a magnetizing current of 10% has been added to the elements Y55, Y66, and Y77, and subtracted from the elements Y56, Y57, Y65, Y67, Y75, and Y76. This admittance can be calculated through the same process we used for the single-phase transformer. Pay attention that for this case, we have to use a base impedance for the delta connection. If you want more information about this transformer modeling technique, you can search for a paper entitled An Example of Three-Phase Transformer Modeling for Distribution System Analysis on IEEE Explore, written by Mr. Dugan, currently with EPRI, and Professor Santoso, currently with University of Texas at Austin.